I'm gonna draw a picture, and you should probably draw a picture too. Here's you guys know what a seesaw is?
Yeah.
Always have to double check it. Oh wait, you're not quite in the iPad generation of kids that just didn't touch graphs. So here's a map
We're doing physics
in
one.
one, and here's another math. And here's the fulcrum of this seesaw, right? So the idea is this distance is d1, and this distance is d2. And so this seesaw is going to be balanced when m1 d1 is m2 d2, right? So you got your equal and so what happens is what we do, we extend this idea to actually do it on this side of the board. So we extend this idea in general to an x-axis, right? Where we can place a mass. So here's some mass here, and we can place some mass here. And then somewhere in between them is going to be the center of mass, which sent that location of the center of mass will be called x with a line over. And so if this is x1 right here, and this is x2 to go with like if m1 is gonna have x1, m2 is gonna have x2, the center, so the relationship to the center is our d1, right? And the relationship is d2. So this equation still holds. It's just now we can make a slight modification because we're on this axis. So I could say, okay, well, m times d1 is this distance. In other words, which one's bigger? Which one's further to the right? Center or x1? And this is further to the right. So we'll take this and subtract the x1. And that's d1. d2 is going to be x2 minus the center location. So we get x2 minus x bar. And now what we're going to do is we want to solve for what this location x bar is with respect to the information that we would have. In other words, the masses and the distance. And so, yeah, I don't need my notes. Okay. Distributive property is going to give mx bar minus mx1. Oh, I forgot to put an m1 here, sorry. So m sub 1. And then this is equal to m sub 2 times x2 minus m sub 2 x bar. Bringing all of the x bars over here and kicking the constants over, I have m1 x bar plus m2 x bar is equal to m1 x1 plus m2 x2. And then factoring out the x bar gives me m1 plus m2 times x bar. And I still have m1 x1 plus m2 x2 over here. So that when I divide and isolate, I get where this location is. I'm going to get x bar. So I can always compute where this point is on the x-axis, so long as I have the m1 x1, m2 x2 information. It's going to be this interesting dot product kind of thing. m1 x1 plus m2 x2 all over m1 plus m2. In English, you can interpret that to be the sum of the moments divided by the sum of the masses. And I'll specify that vocabulary here, just so that it's on the board somewhere, so that the MIXI is what we're calling a moment. So whether that's M1, X1 or whatever. And then also this X bar is the location of the center of mass. This is the location of the center of mass. Okay, any questions? Good to erase? Okay. No sweat. Just let me know. Bella, you good? Okay. Did everybody get what they wanted? Oh. I do have a fun fact for you guys. I pirate a lot of this stuff straight out of the textbook. Whoa. So in the event that you do miss something, there's a 99.9% chance that if you open the textbook to the section, you'll be like, it's right there. Now, granted, some of this stuff I don't give, or at least the textbook doesn't have, because I mean, this is why you pay for a personal instructor to actually take you through stuff. But okay, but we good? Okay, because now in classic Calc 3 fashion, we'll extend the idea to just more than the boring old single dimension kind of, okay? When we generalize that idea, you can see that we'll have now m1 times x1 minus x bar plus m2 x2 minus x bar, and so on and so forth, right? This is just going to keep going. And if we have decided, let's do this with n objects, right? So instead of just 2 objects, we'll do n objects. So I'll stop at the nth mass, and then I'll have this xn minus x1. I can make that so much easier with the summation notation, right? So k equals 1, stop it at n of this construction of m sub k's with the x sub k difference with every bar. And then that is what we're setting equal to 0, because this is essentially the equivalent step of kicking everything over to one side of the equation. So that when we solve for x bar by analogous algebra, we're gonna have x bar given by the m1 x1 plus all the way up to n xn. So sum of the moments, again, in English, sum of the moments over sum of the masses. M1 up to n. Oops. And we can give this in a much nicer notation with the summation stuff, right? We could say that this is just the summation from k equals 1 to n of the moments m sub k x sub k over the sum of the masses. So m sub k. And if we recall, that mass is given by this product of density and then d, right? Is that we can then approximate our m sub k with a density function evaluated at the x of k times that change in x. That would be the approximation of d. So right now it's an approximation that we can turn into something. So it's we're trying to get into discrete land into continuous land. And this is going to tell us that we can put x bar is equal to the sum k equals 1 n. Instead of doing m sub k, x sub k, we're going to start moving toward with respect to our density. And so m sub k, we can just substitute this in. So rho of x sub k times delta x, all of that times x sub k still on the outside, because all I did again is replace the m sub k with this all over the sum then of k equals 1 to the n of rho x sub k delta. Because again, m sub k we're replacing with this approximation in our sum. And now it's starting to look like something we could do calculus with. Because we can make this delta x be grow to 0. So we could say for continuous density, we're gonna let this change in x go to 0 as our n goes up to infinity, right? So it's the same exact thing as we do with like of the very beginning of Calc 1 with Riemann sums and integrations. We'll do that. And so we can rewrite, and we're going to the limit of this. So x bar is going to be the limit as this delta x goes to 0 of this ratio of summations. And so I'll just plug in this right here. We have the sum from k is 1 to n of rho of x sub k delta x times x sub k. Okay, over the sum from k is equal to 1 to n of rho of x sub k delta x. And now, with the limit properties, if you take the limit of a quotient, that's the same thing as the quotient of the limits. So I can say, I'm going to have now the limit as delta x goes to 0 of this guy. And notice I'm going to rearrange this. I'm going to put this x inside because that delta x is going to become the dx. And I have this sum of k is equal to 1 to n of x sub k times my density evaluated at x sub k. That delta x out the n is going to turn into a dx with this delta x going to 0. And then at the bottom, we still have a limit delta x going to 0 of this summation that's pretty much already given in a Riemannian way description of rho x sub k delta x. So you see how this is basically just an integral, right? We're taking this partition size down to 0 over this. So we're going to get an integral from a to b, and that integral of the distance that we're going over our density for, of x times the density function, dx. So that x that rho, and then the dx, this is going to 0, it's differential. And we have a ratio of integrals, so a to b. This is simpler, we just have the rho and b. Questions, comments, concerns?
We have to know this. Do an exam.
Not for the upcoming exam, but this is probably gonna be on the final in some way, shape, or form, maybe. And also, this is statics. Yeah, so either way, as a professional engineer someday, I would hope this is something you seek to gain mastery over. Especially if you're building things that need to stay balanced. I'd rather not go over a bridge that was built by engineers who decided that this was too difficult to learn.
Sums are pretty hard.
But are we good to erase? Okay,
No.
let me know when, because all that's really left is now we're going to extend into the double integrals and triple integrals, because right now we're still only talking about if you were doing center of mass problems on a single line. But that's pretty boring, and I'm pretty sure most things you build aren't just one linear dimensional, right? You're going to have things like plates and odd shapes, two-dimensional objects that you're going to want to balance and other things like that, knowing where their centroids are. Three-dimensional objects, where's the center of mass going to be in something with 3 dimensions, etc. So especially with rotating bodies and other things like that. But with this construction, notice that we've gotten to calculus and we started with a playground seesaw. Okay, so the idea is technically, if you were on your own time and you had a friend say, hey, blah, 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 I went to the playground and I'm sitting on the seesaw, and then you can traumatize them because you remember, you can start with the construction of M1D1 equals M2D2, but hey, guess what? You and your friends calculate your moments so that you could get those equals, so that you have center of mass in the beginning. And then you could say, imagine now we had n people sitting on an infinitely long seesaw, and then you can construct bam, 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 and then say, oh, let's account for our body density, because why not? And then you can account for density, make the approximation, take the limit as calculus. Now you just have continuous integrals. Okay, so if you think about math going, that's why I say my memory is bad, but I'm good at math, because I just need to know the seesaw, and all of this comes for free. Just a matter of what you're willing to poke at, what you're willing to generalize, and then what you're willing to play with. And So yeah, learn math that way. So don't try to just memorize this board. It's a horrible idea. Memorize the seesaw, memorize the idea that you want the moments to be the same for balance. And then think about extending it. So that gets you going, then extend it once you see kind of how it's supposed to mechanically go. And then it gets you to where your end destination. Okay. So. That's a pretty board. I did not plan on that turning out that good. Okay. Let's see. You guys ready for the definitions now? For the moment. So the reason why I spent time on this is because lots of the formulas are essentially just like reinterpretations of this exact same scenario. Just extended now in different directions. So nothing crazy. If you happens to be in polar coordinates, what is dA?
Already on the data.
You happen to be then extend that to cylindrical, what is dV?
All square. Square sum.
Everybody plus.
Oh, data.
That's sphere. So cylindrical is going to just be
Easy,
RDA. Yeah. What is this? It's like the Pavlov's dog. It's just every single time I say DV, it's like, oh, goes there inside me.
Oh, my God, comparisons.
Actually, do you still remember that one? So if we are in spherical coordinates, the spherical
Oh,
DV
square
is.
sum.
Yeah, there we go. Okay. Let's see. Definition. We're gonna let rho be an integrable density function. On some closed interval, right? Then the center of mass. Center of mass is located at the point x bar given by the formula big M over little m, where the total moment, is big M, and the mass is represented by with R. Then there's our two formulas for it. So compare this with the notes that we just did. You'll find them to be very, very reminiscent of each other. We're calling big M simply when we did the integral of the moments. Basically, sum of the moments involves x times density, right? X rho dx. So this is the numerator of what we just did, of what we extended the idea. And then the mass, a little m, is just going to be like the denominator of our extended idea, right? The sum, but only of the density. So technically, you already saw the pieces. Now we're just giving it English words. So when we're referring to center of mass, now we know what that location is, that ratio. And then we just call these M, the big M, the total moment. This is in R, okay? So this is all in one dimension, it's R. And we're going to extend the idea. Let's see, do I want to put that on a French board? Actually, yeah, let's do a fresh board because then I can really emphasize how similar the double integrals and the triple integrals are. Okay, so let me know when you've got this definition written down because we're gonna go off all the parallels for the definition extended to R2 and R3. I'll probably do R2 on this side of the board, R3 on the side of the board. Okay. Thumbs up if we got it. And again, if you don't have it, guess what has it?
Textbooks.
Yeah, pretty common too.
The organic super.
Okay, so let me look at the board. And I want. Over here is going to be R2, all right? Over here. Oh, that's such a good part. Well. This is going to be R2. This is going to be R3, okay? So in R2, you have two dimensions now. So your center of mass is no longer just going to be that single x coordinate. You need another coordinate. You're going to have an x coordinate and a y coordinate for your center of mass. So we give that by x bar. So the x bar is going to be something. It's not just going to be big M by itself. It'll be big M sub y over little m. And the y coordinate is going to be big M sub x over little. And the reason it's subscripted that way is for the reason what we call it. My is the moment with respect to the y-axis. So that's why we subscript it with y, even though it's going to be the x coordinate. And then the y coordinate is getting the moment with respect to the x coordinate. You can think of, so when you're memorizing these, just know that it's the other axis that it's going. But what we do have then is for my, the moment with respect to the x-axis is going to be related to finding this. So this is going to be, instead of a single integral in R2, what do you think it's going to be? Double integral. Wow, you guys can count to 2. And then the region R, whatever that region might be instead of an A to B. And so since we're using this to find the x coordinate, so we're going to use the same kind of construction. X times the density, where the density is now a 2-dimensional function. What's the differential going to be? Yeah, well, just generally speaking, dA, right? So if it's ambiguously given, you can just use dA or whatever. Or I should say ambiguous, generally stated. Okay, so then take a gander, given the parallel structure of everything, what the moment with respect to x is going to be. Density. What's going to be in the integral? Yeah, why? Right? Because if the x coordinate we multiplied by that x for the moments, all the x m's, right? Then moment for y, all the moments for y is going to be y m's, right? So y times the density dA. So don't get those switched up. And then of course, this is going to be true for the both of them. Is that, well, the idea behind the mass is always going to be the same. Little m is just going to be the plain old, no variable added, just the density by itself. And that's going to be the mass. So if you're doing a problem like this, which you probably have if you're in statics or whatnot, is you kind of do these, you treat these separately. So I would find this separately, I find this separately, I find this separately. Once I have the pieces, then I just kind of, this is why I didn't put this on the upcoming unit exam. There's too many concepts for me to be wasting your time to compute 3 double integrals just to solve 1 question. Okay, because this is not hard. It's just boring. Yeah, so I generally like to do not boring mathematics. And this classifies as boring. So if basically if it's one of those things where you can just get the first piece and then using a little bit of common sense derive all of the rest of the formulas, kind of boring. So here's how we do this in R3. How many coordinates? If we have 2 here in R2, we have 3. So x bar. Now think about this. I want you to see this logic. There were 2 total variables, x and y. When we did the moment, instead of subscripting with the variable that was going with the coordinate, we took the variable that's not. What are the variables that are not x?
Y and Z.
There you go. Put that in alphabetical order and you got yourself the formula. Very difficult. Okay, and then y bar, what's the moment gonna be with respect to?
X, Z.
Yeah, just whatever is not in there, so x and z, and then over the math, and then the z coordinate's gonna be what?
Y, X.
X, y, yeah, because those are the two variables that aren't z. So do you see how I'm trying to get you to think? When you're learning this stuff, find those kinds of patterns, because lots of times that motivates, or at least helps you with the way that things happen. So R2, double integrals. R3, what kind of integrals do you think you're gonna have?
Triple.
I know, very trick question, I know. So let's take a look at the moment with respect to the YZ plane. You said it's gonna be a triple integral, right? So we have a triple integral. Now, over here, here's the pattern. This moment was used to find which coordinate. Yeah, and so we put the x there. This moment was used to find which coordinate. So we put a So should it be a stunner that this moment is used to find which coordinate? So. And then from there, I should theoretically be able to walk away from the whiteboard and you fill in the rest of the formulas. Notice we're using dV, just a general volume differential for this. Okay, so the moment for x and z, this moment is used to find which coordinate.
Y.
Okay, so we have a triple integral because it's in R3. What's going to be the integrand?
Oh, wow.
Yeah. Y rho. And then now we just have a third one. So the moment with respect to the xy plane is for which coordinate? And so what's the integrand going to be?
Z rho.
Math makes sense. It's patterned. Okay, find the patterns. Make your life easier. Don't memorize brute force. And then of course, so if mass here said, okay, I don't care which coordinate you are, I just want to sum up over the density, what do we think little m in 3 dimensions is going to be?
This.
So this is why I don't do formula sheets. You don't need it. If you sufficiently practice the concept, then you have it. That's pretty much so. Realistically speaking, just for how time constraints work on an actual exam, probably on the final, at least one of these is going to be given to you, just because it's just too much. There comes a point when there's no use in testing you over the same double integral over and over and over again. So there'll be probably one that I'll have you do by hand, but then just give you like an ass or something like that. So then you can push. So you can find like the coordinates. There is a vocabulary word that you need to know. And I think, yeah, I'll stick it right here. So if rho is constant, so whenever you see in a textbook, rho is constant, my brain says, just say rho is an R. And I'm saying specifically R plus. Why am I saying specifically R plus instead of just generally a scalar R? I mean, yeah. In pure math world, we could say, haha, it works in theory, but when you're making something in reality, right, it's just going to be some positive. And then if we have it constant, then the center of mass is called something specific. We call it the centroid. It's called the centroid. Centroid. Okay, so if rho is constant, all right, so either looking at the double integral or the triple integral idea, it doesn't matter. If rho is truly constant, does it vary with x? Does it vary with y? In the third, does it vary with z? No, it's a number. Numbers can be brought out. So what effect does the density actually have on the way the integration is going to be formed? None. So the moment you have constant density throughout an object, just disregard it. And so then it becomes irrelevant as to telling you location of where that's gonna be. And so that's why we have the convention, is if you're asked to find the centroid, don't even bother about the density, just choose the most convenient one, which is the number one, right? So then that way you just have to do an integral with respect to an integrand, that's just 1 times dA or 1 times dV. So if you're asked to find the centroid, make your density 1, because first of all, it doesn't matter. It's a constant that's gonna be pulled out. And the way that the ratio is gonna work is that we're just trying to find locations, not magnitudes of anything. So does that make sense? So if you see centroid, that's why you can just say, okay, the density is just 1, I'll use that, because that's the easiest possible integrand to do the integration. Cool, and that's why this is specifically positive reals, because 0 is not allowed. Don't throw 0 in and say, haha, 0, and move on, okay? 0 density is kind of meaningless in a physical application. So as long as it's a positive constant density, find the centroid, make it 1 so that you pull it out, it's really easy. Make sense? Okay. Well, in that case, so there's one more section left that's going to contain exam content on Wednesday. And then Friday we'll review, and then Monday you've got an exam on chapters 15 and 16. Do you guys have exams for the other classes this week?
Yeah.
Okay, the statics one on Wednesday, right?
Yeah,
Okay, and then, but after that, it's then getting ready for calculus, right?
pretty much.
Okay, so obviously get ready for statics because there's a lot of volume there. But don't come to Friday having not actually started the process of reviewing for chapters 15 and 16 exam. That's too much volume to realistically expect yourself to be able to get anything out of anything. If you don't start that process on Thursday. Or preferably after your exam from statics. So I will be doing an exam review over the weekends. Yeah, I gotta figure out a way to figure. What generally works? Saturdays? So after 4 on Saturday? Okay. Raise your hand if you could do Saturday at 5 o'clock.
Checking, so I'll try to get that shit covered. I'll find out that.
When does that shift normally go to? Can we push it back later and it'd be fine? Or is it closing?
It's a closing.
It's a closing.
Soon, we're supposed to go at 5, except for attendance, so it's anywhere from 5 to 1 AM.
Okay, wait, let me stop the recording for a second.